Am I audible, guys?
Yes, sir.
Yes, sir.
Okay. So I think one topic left in the last lecture, which is the conversion of graph, right?
Yes, sir.
So we'll start with something simple. Imagine a PV graph is given to you for a cyclic process. And you can easily identify that this is either isobaric or isochoric process, right?
Yes, sir.
Yes, sir.
So we have only two process, isobaric and isochoric, right? And you're supposed to convert this into VT graph and PT graph. So we have VT graph and PT graph. Okay. So because we have to plot only two graphs, isobaric and isochoric. First of all, we need to understand that in the VT graph, what is missing? Which axis is missing here? The pressure axis, right?
Yes, sir.
So how the constant pressure will look like in a VT graph? See, we have two processes, isobaric and isochoric. So that's not an issue. So we know that inherently that we have to draw two lines for isobars. So we need two isobars, right? Like this. But how to do the sorry, this is the iso course. So the two iso cores I have drawn for the DA and for the BC process. Tell me how the isobars will look like in a VT graph. So in a VT
Straight
graph,
line, sir.
is straight line passing from where? How we draw isobars? Pardon?
Sir, passing through, you mean like a certain point?
I mean, how you will draw that line? Horizontal, vertical, slant, how you draw?
Sir, slant with a slope of NR by P.
Yeah, very good. So it will pass through origin, right?
Yes, sir.
So the isobars we have already discussed will pass through the and the quadrilateral which is formed. This is your cyclic process looking on a or appearing on the VT graph. That's it. And it should be taken care that okay, it is passing through the isobars are passing through origin. Now high pressure will look on which axis? One or two? The high pressure is which one?
Two, sir.
Two.
So because the high pressure means lesser slope, right? NR by P. And now let's talk about the first process. The AB is what? AB is which process?
Isobaric.
In AB, the volume is increasing or decreasing?
Increasing.
Increasing.
So volume is increasing. So I think this is possible. Oh, sorry, not this. Volume is increasing from A to B. Yeah, so A to B is high pressure and the volume must increase. So can you say A to B is like this? Do you realize this?
Yeah.
High pressure with increasing volume. So once I get the A to B, just think of any one, you will get the answer. So B to C is what? Isochoric
Choric.
process. And in B to C, pressure is
Decrease.
Decreasing.
pressure is decreasing. It means you must go from 2 to 1, right? Because 1 is at low pressure and 2 is at high pressure, if you remember.
Yeah.
And rest is done. Once we get these two, this is your process. And what you can see that the clockwise cycle in PV has become now anti-clockwise cycle in VT graph. Is this clear?
Yes.
sir.
So A, B, C, D. You can now verify. So C to D is what? C to D is isochoric. Sorry, C to D is isobaric,
Yes.
and volume is decreasing.
Yeah.
And it is happening that way only, right?
Yes.
So given the PV graph, it is very easy to convert into VT graph. Similarly, you can plot the PT graph. Can you do this? Try once.
Yes, sir.
Then I'll show you. Okay, I'll not do anything. So try and see. You have to make sure that the arrows are correct. Okay. Please do it.
Sir,
Yeah, tell me.
sir, it's the same graph as the VT graph, but the direction is reversed.
Okay. Yeah. Graph will be similar only. So we have to do 2 lines from the origin. And these 2 lines will represent what?
Volume.
Volume.
Volume. Constant volume, right?
Yes.
In a PT graph, the missing axis is always passing through origin as a constant value. And then do 2 lines. And now we are done. Just a minute. And so A to B is what? Which process? Isobaric.
Yeah.
Yes,
And
sir.
it is high pressure, so A to B is like this only, isn't it?
Yes, sir.
I think the rest is obvious. So A to B is there. So C must be here only. Right?
Yes.
So is this your graph with
Yes, sir.
exactly matching the A, B, C is matching this way?
Yes, sir.
Yes, sir.
Okay, so that's pretty interesting and easy. So they may give you the reverse graph also. So I have given the easy and then asked you the difficult one. Okay, solve this question, everyone. So I'm giving you VT graph. And now we have, you can see the process. A. Tell me which process is A to B
Isochoric.
and B to C
Isobaric.
and C to A.
Isothermal.
You can see there are three processes now, right?
Yes, sir.
Can you plot the PV and PT graph because VT is given? Plot PV and PT graph, please. So you plot first, then I'll plot. PV. So once done, let me know. Then you can match the answer. I hope it is done now.
Yes, sir. PV graph is done.
So by default, I will do the. Okay, we have only one axis, right? Only one ISO. Okay, this is PV graph. Now this is. Wait. Okay,
Just
we can't.
straight line
Yeah,
won't
this is
come.
nothing is required. Nothing is required. So in the PV graph, we can draw direct, right? It's a VT pressure. Okay, no. We need constant volume, right? Okay, this is already there. Volume is there. Yeah, that's fine. Okay, sorry. So now here the AB is which process? In a PV graph, how the temperature isotherm will look like? The isothermal will look like hyperbola.
Hyperbola.
Yes, sir.
And as you can see, from C to A, the volume is at constant temperature, the volume is increasing, right? So C to A must be like this.
Yes, sir.
Now we have to think of the other two processes. C to A is done. A to B. In A to B, what is happening? The
Yes, sir.
volume is constant. Volume is constant, no?
Yes, sir.
So volume is constant from A to C. Sorry, A to B. We are looking for A to B.
The line perpendicular to the x-axis.
And then A to B volume is constant, but A to B is like this only.
Ah.
So the problem is you have to think about whether it will go down or up.
Then it will go up.
In this case, A to B, if you look carefully, the temperature is increasing, right? At constant volume, temperature will increase only when pressure will increase.
Yes, sir.
See, you have fixed the volume. Okay. But as you go from A to B, you can see in the original graph, temperature must grow, right? And that is only possible when you go in higher pressure, right?
Yes,
So
sir.
now we are done. So A to B and B to C is anyway isobaric process. So is this your graph? Can you check?
Yes, sir.
Very good. So you all got this graph, guys? Tell me.
Yes, sir.
Yes, sir.
Yes.
Okay. So can you do the PT graph? PT is, I think, easier only. I mean, of course. So in PT also the iso core will go from origin. So I think you can draw one line because we have only one isochoric process. And the rest you can draw. Okay. So I think isochoric is A to B. And when you go from A to B, the temperature must increase, right? So the AB will be the slant itself, right? Hello.
Yes, sir.
So I think this is your AB.
Yes.
Because when you go from A to B, temperature is increasing. So we are able to identify AB directly. What is BC? BC is
Barik.
isobaric, so it will be a straight line.
Yes.
So you know the BC is like this. But which way? Right or left? Tell me guys, right or left?
Sir, left.
Left.
Very good. So it is indeed left. And then so this is how you can think about. Okay. The last question, then we are done with the graphical practice. So this is P. Have we done this question? No, this is we have done. We have done the PV graph, right?
Yes.
But now here it is.
PT.
And how many isotherms and how many isobars we have?
2 each.
2 each.
So first, before you plot the graph, you have to draw the 2 isotherms and 2 isobars. So you are supposed to plot the VT and PV. I think you can do it. I mean, no need for me to intervene. Please do it. Plot the graph. And graphical question will come. Let me tell you, in JEE Advanced as well. Oh. Are you guys writing papers? JEE-Mains PYQs, like paper, complete paper?
Yes, I have started some.
Very good.
Yes, sir, done.
Very good. So let me verify the. So which graph first should I draw?
VT, sir.
VT. Okay. So because VT graph is not having the pressure, so we must draw the 2 isobars first, right? 1, 2. So AB must be on which axis? The below or the, sorry, which slant? The top or the bottom?
The bottom.
Bottom. And while going from A to B, the temperature must increase.
Yes, sir.
So I think this is the AB. So B to C. What is B to C?
Isothermal.
Isotherm. Okay, I need to make this slide. Yeah. So in B to C, what will happen? The pressure must decrease.
Yes, sir. The volume will increase.
Temperature is constant. So when volume, when volume will, B to C is pressure is decreasing. So volume must increase, right? To keep
Yes,
the
sir.
PV constant. So it will be above, right? Hello,
Yes,
guys, tell me. And then again, C to D is decreasing temperature. I mean, once you draw the few parts, it's obvious. So A to B, B to C, C to D, and D back to A, and you can see this diagram. Okay. So you all are getting the same answer?
Yes, sir.
yes, sir.
Yeah.
Yes.
How the PV will look like? So in PV, the isotherms will be, you know the answer. These are isotherms.
Hyperbola, sir.
Yeah, so I put two hyperbolas,
Yes, sir.
Yes, sir.
and the farther the hyperbola, more the temperature, right?
Yes.
So
Yes, sir.
BC will be on the outer one,
Yes, sir.
and DA will be near, like close to the origin, right?
Yes, sir.
Anyway. And the isobars are obvious. So I think you can see the graph itself. Huh? Okay, AB is what? When you go from A to B, the temperature must increase. So AB must be like this. Because this is low temperature, this is high temperature. Hello, tell me.
Yes, sir.
Yes, sir.
Yes, sir.
So we got A to B, I think then rest is okay. So I hope this is your answer.
Yes, sir.
So I think this is done. Okay, so I mean, there is no end to the question. I mean, you can keep on plotting as you wish. But if you have understood the basic nuance of plotting the graph, you can always plot that even difficult graphs. So the conversion is basically, I mean, you can expect in advance, less in mains, I would say. In mains, you can get question from the efficiency and so on. Anyway. So now we can move to the last topic from thermodynamics. So we have second law of thermodynamics. So why we are going to study second law?
Because
Because
first law.
yeah, first law is not able to answer something. Now guess
Yes, sir.
what first law is not able to answer?
why does a system tend to become disordered?
No, first law never answers that why.
Sir, it does not answer that.
Yeah, I mean, the thing is what nature wants. First of all, the first law never tells what is nature behavior. First law believe that we can create a process such that the efficiency can be 100%, but it is our common experience that no system can be designed with 100% efficiency, right? So in every
Yes.
system, the loss is inevitable, right? So apart from the target system, we always need surrounding. Is it possible to have only system without surrounding?
No, sir.
So you have a target system, you target somewhere, but you also need surrounding with proper interaction so that whatever you do, whatever is getting consumed by the target system is consumed, and the rest part of energy can go to surrounding. So the nature is only able to work under two reservoirs, you can say. Nature cannot have the, I mean, any natural system, any realistic practical system cannot be 100% efficient, no matter what. So the first thing that first law failed to explain is that why, I mean, first law never says that, okay, 100% is not possible. It says, yeah, 100% is also possible. But in reality, in practice, we know that 100% is not possible. We cannot design any such engine which can do so. So second law of thermodynamics is basically our real life, the life in which we live. The other thing is, which first law do not explain. We all know that, okay, this again, it's our common experience. We all know that heat can flow from high temperature to low temperature. We know this as per the common experience, but do we know why? So heat goes from high to low naturally. But do we know why it goes that way naturally? Why heat doesn't go from low to high naturally?
Sir, because it wants to create a uniform temperature.
Yeah, maybe. But the question is, what drives to create? I mean, that is the question, that what is the driving force behind this creating the equilibrium?
Entropy.
Of course. So the nature is in the constant endeavor to increase its entropy as much as possible. So when we have a high temperature system, it is already very random. But what about the low temperature? It will have a less randomness, right?
Yes.
Now, when you add some heat from the high to low, of course, the high will lose the entropy, but low will gain the entropy. But if I can prove that the low will gain more than what high will lose, the net entropy of the system who are exchanging the energy is increasing, isn't it?
Yes,
So
sir.
they say high is losing energy, high is losing energy, and low is gaining energy. Question is, the loss by the high will decrease its entropy. That is perfect. And the gain of energy will increase the entropy of the low temperature system, isn't it?
Yes.
Yes,
If
sir.
the gain is bigger than the loss of the high temperature, the overall entropy is increasing, isn't it? So it is the and what is entropy? I have explained entropy in the very first lecture. Entropy is basically the nature wants symmetry. So randomness is a way to attain symmetry. So nature will never make itself ordered, because by making ordered, you kind of disturb the symmetry of nature. It is the biasness which you bring, and nature is unbiased. So let me demonstrate a simple example. Let's say you go to any vegetable market, okay, or any market. You see there's so much chaos already. There is so much, chaotic movement. Person is going from here to there, there to here. Okay. And there is a commotion everywhere. And there is a natural noise. Okay. So a market area will have a natural noise, isn't it? I hope you can understand the noise part.
Yes, sir.
And let's say the crowd is huge and then someone farts. What kind of disturbance you will create by doing that action? Will that disturbance will be felt by everyone else or only the nearby one? So the answer is obvious. Okay, no need to answer. You know what will happen. So the chaosness, you can say the randomness or the noise level, are we changing the noise level by significant value? The answer is no. Isn't it? Are we changing?
No.
Imagine that you are sitting in a library and the same fart. Can you imagine the disturbance you have caused? The scale, the magnitude of disturbance? So someone may be embarrassed for the life also. So it's a pin drop of silence. In a silence, a smallest disturbance is felt in a most significant manner. So the same fart is like energy. So the same energy released in the high temperature, which is like high noise, will create a alteration in the disturbance by less value, isn't it? But the same energy when released in a low temperature system, which is like silence, the change is bigger. Do you realize this?
Yes, sir.
So whenever a hot body is giving its energy to a cold body, it is definitely losing the entropy, but the loss of entropy is very small. But the same energy when received by the cold body, the change in entropy is very, very high. And because the overall change is positive and the nature is trying to optimize the entropy of the universe, so this is happening. So the whole idea is a system and its surrounding, when system is losing the entropy, its surrounding is bound to gain the entropy. If surrounding is losing the entropy, the system is bound to gain the entropy. But if either of the phenomena is natural, it is not, kind of forced. It means nature is trying to go towards a bigger randomness, a bigger symmetry, a better symmetry, I would say. And hence the word entropy is introduced. Entropy is the measurement of symmetry. Okay. So when I say high entropy, a system is higher level symmetry. It has attained the higher level symmetry. So more the randomness, the system, the nature will become more symmetrical, isn't it?
Yes, sir.
Okay. So that symmetry is actually having this technical word entropy. And from the common experience, we know that every natural process having this constant endeavor to move towards the greater entropy. That is the natural process. Is this clear? So why heat flows from higher temperature body to a low temperature body? The answer is because that process is trying to attain a bigger value of entropy, that process is trying to attain a greater symmetry, and that system is going to be less biased. The way you want, you can explain. Is this clear?
Yes, sir.
So second law was actually introduced to overcome the drawback of the first law, and the first law was not able to answer that the efficiency cannot be 100%, why natural process occur the way they occur. So as per the first law, energy is conserved in either way. See, even a cold body is giving energy to the hot body. The energy of the two systems is conserved, isn't it?
Yes, sir.
See, hot is giving to the cold, or cold is giving to the hot. In each case, the energy is conserved. First law is about energy conservation. So energy conservation cannot tell you the direction of propagation of energy in a natural system, isn't it? So this direction was, the issue. So energy is conserved in either way. Either hot is giving to cold or cold is giving to hot. In both cases, energy is conserved. But the problem is the nature is able to conserve energy, but we are failing to get the question on this answer, that why natural system having only one way of energy flow? Why not the other way around? Because even if it is other way around, there is no effect on the energy conservation. It means we need something more deeper away from the concept of energy conservation, which can tell us the direction part. Okay, and this is how we came to know about the term entropy. So entropy is the way the life is designed. So every natural system inherently is following this process since time immemorial. The universe is constantly increasing its entropy, and the moment the universe will have the infinite entropy or the maximum entropy, the universe will collapse. That is the dead end of the universe. So in a way, universe is also running perpetually towards the greater entropy. Okay. So in our day-to-day life also, see, as the generation is changing, we are coming out of the industrial revolution, then many generation has passed. Now it's a generation Z, X, Y gone. Now this is generation G, next will be generation G plus. As the generation is moving, you can see the chaosness of the civilization is also increasing, isn't it? Now people are having more random choices. Okay, no one is trying to bind by the rules. You can see clearly that the nature is getting dominated, and with the progress of generation, this randomness is growing rapidly. It is going to be difficult to control. Anyway, so this chaosness is part of not only thermodynamics, it is part of your day-to-day life. In fact, it is a natural way of thinking also. Like you can always think that, okay, which process will occur and why it will occur, only on the basis of energy conservation plus entropy. Energy conservation is required to make it physically relatable, but the entropy will give you the sense of direction. So nature is following this rule inherently. So in the development of second law, there were some statements given about this second law, and there are many statements given. We will only consider the most famous of the statements, because see, this is a philosophical thing. If you look at second law, it is purely philosophical, and because it's a philosophy, so everyone came with their own idea of explanation. Out of many ideas, two is preserved as a standard de facto, and that two I must quote here. There are two famous statements. See, the way I gave the one statement, what I said, entropy is the measurement of symmetry. Now this is my definition. So you may see this definition in literature, maybe after some time. I mean, someone will write this for sure. But in the very beginning, someone said something about the entropy, about this second law, in the context of course, heat engine, because it is all about the engine. So earlier, the steam engine invention was the biggest revolution, and that was the beginning of the industrial revolution part. And then the steam engine was not efficient. It was a very poor engine, you can say. So Sadi Carnot was the, you can say, the father of the modern engine, you can say, and he designed this engine. He wrote the philosophy, the working mechanism, and he was the the person who actually gave the idea of 4-stroke engine. And based on his idea, of course, his idea was not practical, so he was never able to implement that. But taking his idea and making some tweak to his ideas, many engine came into existence, like Otto engine, which is based on the Otto cycle. We have diesel engine, which is based on the diesel cycle. Diesel means the person name is Rudolf Diesel, and in his name these are cycles began. So these all came from there. Okay. So let's formally put it across the two famous statement. The first we call Kelvin-Planck statement. So Kelvin-Planck statement, and see, if you read the history, it's a very beautiful history about this. I mean, there was a guy who was working on an artillery workshop, and before that there was a theory called the caloric theory. So people think that, okay, the heat is like a invisible fluid which flows and follows certain rules. Okay, it flows from the high content fluid to the low content fluid. And what he said that, okay, see, that high content fluid means a high temperature body will have more caloric than a low temperature body. So when you touch each other, then just like the water goes from the high level to low level, this also goes. But I mean, this theory was rejected after some time, and we actually came to know about the first law. And then we got more fundamental. I mean, this law got refined over the time by the Sadi Carnot and Clausius, Joule, and many other, you can say, visionaries. So in the Kelvin-Planck statement, what we are trying to say is, if you want to design a heat engine, okay, which is working in a cycle, then it cannot be 100% efficient. That's simple. If you want to design a heat engine which is working in a cycle, which means it is working continuously, repeatedly. Okay. So it is following certain steps and it is repeating those steps again and again and again. And in a cycle, the benefit of cyclic process is only a cyclic process can be more efficient. So if an engine is working in a cycle, then we cannot create any practical engine with 100% efficiency. Okay, this is the first statement by the Kelvin and Planck. Okay, in other words, you can say, okay, it is impossible to convert all work, I mean, all heat into work. So all heat cannot be converted into work. So some heat will convert into work and rest of the heat will dissipate or will be thrown out, will be lost. So every vehicle which you run, drive, ride, every vehicle will have exhaust, right? What is exhaust basically? Because the engine is working in a cycle, the fuel is giving the energy. A part of energy is consumed by the engine, which drives the vehicle. The rest not used, not consumed energy is thrown back to atmosphere, and the atmosphere is the natural heat sink. So you can see our atmosphere is the natural heat sink, and the car or the bike engine or the truck engine or the train engine or the plane engine, what is your engine? It is the source actually. So every engine is attached to a source, That source's job is to create energy, maintain the high temperature, correspond to the surrounding, and so it will be using some energy and will throw back the rest of the energy. So a car or a bike or something like that will have a different efficiency in different environmental conditions. So let's say if you're driving a car which is made in India, and somehow if you are able to drive, because it's very difficult because the all the fuel will frozen there. So they use a different fuel, and I hope you have studied the Van Hoff factor, right? How you can change the melting and boiling point of a solution by adding some impurity or something, right?
Yes, sir.
Yes,
So
sir.
they also do the same thing. That is actually essential thing. They lower the temperature of the fuel such that even at minus 20 degrees Celsius, the fuel is intact. It is in liquid form, which you can vaporize. And when the exhaust is thrown there, the sink is at a very low temperature. And therefore, the efficiency of the same car engine in the cold countries will be different. In Dubai will be different. In India, it will be different. We cannot have the same efficiency, even though it is manufactured in the same fashion, but the sink will change, and so the answer. So everything matters. Okay. So Kelvin-Planck statement is a way to simply reject the first law that, come on, we cannot design 100% efficient engine. So let me put this into 2 words. So we can say that no heat engine can be designed working in a cycle which sole work is sole or not, which solely converts heat into mechanical work done. Or you can say, in other words, efficiency of heat engine can't be 100%. Okay. Or you can say no heat engine can work with single thermal reservoir. Okay. So the last line is very interesting. What I said is that because you will consume a part of energy, so you are supposed to throw that energy somewhere. What we call somewhere is technically called sink. So sink is a place where you throw the energy. Sink is a concept actually. It need not to be something physical. I mean, of course, it is physical, but need not to be, machine type. The entire atmosphere, the environment, is your natural sink. Imagine that the atmosphere reject your, I mean, it do not accept what you are trying to throw. What will happen? The engine will work. You have consumed energy and you want to throw some energy because you have not going to use that energy, and there is no way to store also. So what will happen? That system will get destroyed if you don't allow it, isn't it?
Yes.
Yes, sir.
So if you go to a party and next day, I mean, you understand what I'm saying, you're denied the permission to use the toilet. Will you survive? Okay, you can't. So we need two thermal reservoir. We need source and we need sink as well, because human body itself is the perpetual engine with efficiency following the which curve? The bell curve. So as you grow, your efficiency first increases, reaches the peak in your youth, and then as you grow older, that efficiency decreases. So you are also heat engine working in a cycle, and the fuel is your food, And technically, if you understand, you're also doing the same thing. No? You're eating the food, which is the complex hydrocarbons or nitrogen compounds, isn't it? So what is protein? It is mostly the composition of nitrogen and all. Nitrogen, hydrogen, oxygen, these things only, isn't it? So everything which you eat is having some molecular composition. And using the catalyst and the digestive juices, we are able to decompose, break down those complex molecules into a smaller molecule. And when you break down those molecules into a smaller part, you break so many bonds. So the bond energy which they have stored is actually released. And that energy is getting stored in the mitochondria or different parts of the body, which is running the body as an engine. And human body is not one engine. We are infinite engine because every cell is actually one engine. Do you understand this? What is happening? And even every engine needs some
Yes.
sync. So at cell level, they release to the environment in the which they are present. Then the body as a global engine releases the unused energy in some form. Okay. So you inhale, you exhale, and you do, I mean, of course, you do so many things, but you are working in a cycle because what you do it repeatedly for a long time, maybe few, I mean, years, maybe up to 100 years also. So we are actually the most complex engine. So every human being is an engine, and we are also working on the based on the second law of thermodynamics. So we are not beyond this. So because we are the engine, we are creating now that a similar engine which can mimic the same process. The food we have changed. So engine will not complain about the taste. And because they are not able to complain about the taste, what do? They can directly eat the, I mean, high caloric fuel. For human, we have to decompose complex compound, and that depends on your digestive power. Okay. Now you know that okay, many birds eat insect. How they survive with the insect? They don't fry it also, but they still survive. Can we survive in the same fashion? The answer is no, because we are designed differently, and they are also designed differently. At the end, whatever they eat, they only consume the molecules. It is some proteins, carbohydrates, and so on. And then they convert into different forms. Okay. So the idea is whatever you eat in this planet, at the molecular level, everything is same. But we are not able to derive the energy from everything in the same fashion as it is done by other species. So we have a different food style. It depends on the geography, your demography also, where you're like born, your food habits which you have inculcated from your childhood. Okay. There are many factors which actually decide what you will like and what will not like. So whoever is eating whatever they are eating, their body is kind of designed to absorb the same. Okay. So the wild animals can do this other things. They can eat whatever they want. Lion can eat anything. The frog can eat insect. Snake can eat the frog, and so on. There is a food pyramid, food cycle, we all know. And everyone is doing the same thing. Everyone is taking the same molecule composition. And at the end of the day, it is the breaking down those complex molecules with the chemicals which the body is able to produce naturally, and then getting rid of the bond, breaking the bond, deriving the energy, and storing in different mechanisms. So that's how everything works in the nature. And our engine is somewhat more dependent one. It cannot consume on its own, so I have to give the energy. So we have the fuel tank, and then there is the entire mechanism which is called the vehicles. I hope this is clear. It's not difficult. The
Yes.
next is called the
Yes.
Clausius statement. Clausius. So what Clausius is saying that, see the nature, we know the nature. What is nature? Nature allows the flow of energy from where to where? High to low, low to high.
Higher to lower.
High to low. But imagine the refrigerator at your home. In a refrigerator, you keep something hot. After some time, it becomes cold or hot or hotter.
Cold.
It means the energy of that object is thrown away from the refrigerator, isn't it?
Yes.
So in the refrigerator, what is the direction of flow of energy? From cold to hot or hot to cold?
Cold to hot, sir.
So is it natural?
No, sir.
No, sir.
And because it is not natural, so is it happening on its own or we are doing it forcefully?
We are force. Yeah.
And that's why we have the force agent is there. That force agent is called compressor. So compressor will circulate the coolant, and coolant will have the inherent property to absorb heat and vaporize itself, right?
Yes.
And that
Yes.
vaporized, vaporized coolant will again come back to compressor. Compressor will take all energy back from the coolant, converts it into liquid, and through the heat sink, which is designed at the back of the refrigerator. You must have seen some wire mesh. Have you seen that? Behind the refrigerator? Okay, you haven't seen. Okay, you haven't
Yeah.
seen the behind part of the refrigerator, right? So if you look behind the refrigerator, somehow you can go and see if it is possible. You can see there is the entire, a wire mesh design. That is the sink actually, and the compressor will throw out that energy, which is taken from the coolant actually. Now, compressor is doing this forcefully, and the coolant is, kind of pressed through the pipes, which is passing through the different parts of the refrigerator. So if you see the open part of refrigerator, if you see some repairing shop, you can see a pipe is running through the wall of refrigerator. I hope you all know this. Anyone has seen this before? Have you seen the pipe of refrigerator? The coolant pipe, have you seen?
No, sir.
In a repair shop, you can see. Okay, you haven't seen. Okay, just a moment. Let me show you. I mean, of course, this is simple. You should know.
Sir, along the side walls, won't the refrigerator be hot?
Yeah, it is always hot. You can touch right now. So
Yes, sir. Sir, but you said that the coolant pipe is running along the walls.
yeah. So it will absorb the heat, na? So coolant is absorbing from inside.
Yes, sir.
Yeah, you can touch the side panels of the refrigerator. You can see, is it hot?
Yes, sir.
Okay, you are checking it right now. Very good. And the same is for the AC as well. Okay, let me show you this. I mean, I've got this simple diagram. Let me share. So can you see this refrigerator now?
Yes.
Hello. You can see this is the behind the refrigerator. This is the sink part. Okay, so from here the heat is released to the kitchen actually. Okay, and the below is the this is compressor. This is bottom. At the bottom you can see there's a big cylindrical object. This is the compressor. You can see the compressor here at the bottom.
Yes.
Yes,
This
yes.
Yes.
compressor. And then you can see the compressor is connected with the pipes, and these pipes are running behind, getting inside the refrigerator, getting into the freezer area, the normal area, the the vegetable drawer area. You can see there are many areas, right? Now, to control, see, if you want more heat to be absorbed, you attach more pipe. So the pipes are running in a zigzag fashion. Depending on the what temperature you want to attain, we have to design the piping. You can say line per unit area. So how much pipe you design put in that area, that will decide the cooling effect. So it can cool much more than you can expect. If you put too many pipes in a freezer area, it will extract more heat, and so it can do the cooling much more than the remaining area. So it's very simple design. I mean, we know the rate of flow of heat and we know the simple physics. What we do is we understand that how much energy we need to extract per unit time so that this kind of temperature is maintained. And based on that, we design the different area, the freezer area, the chiller area, and the normal area. And every area will have different cooling power. So you know that when you put something in the freezer, it gets really cool fast, right? Because we have more refrigerant pipes running there. Okay, this is the heat sink, what we call sink, which is the behind the. And the role of compressor is to convert. It's a why it is called compressor, because it compresses the vapor and converts back into liquid. And we know that to convert a vapor into liquid, we have to increase the pressure and decrease the temperature as well. So this will eject, or you can say reject heat to the surrounding. So when you use the refrigerator, the total energy that is consumed by the refrigerator is positive, isn't it? So if you open the door of refrigerator, what will happen? The reason the area kitchen will get cooler, or kitchen will get hotter. What do you think? What will happen? If you open the fridge, I mean the fridge door forever, the kitchen becomes very hot.
Very hot. Increase the temperature.
Now, this is a very common mistake. The refrigerator is not throwing the energy from anywhere else. See, you take the energy from somewhere and throw outside, right?
So the rate at which the energy is absorbed by the refrigerator increases.
No. When you have a closed system, when you shut the door of refrigerator, you create a closed system. In a way, you separate the surrounding from the system. The inner body, the inner volume of the refrigerator is your system, and outer kitchen is your surrounding. Understood? So what this refrigerator is doing is, it is taking the energy from the food or whatever you're keeping and throwing outside. Okay? Understood what I'm saying? Now, once it has thrown outside, that energy has come from where? The food itself, right? Now, if you open the door, what you are throwing outside will come inside. Isn't it? So
Yes.
there's nothing like outside and inside, isn't it? First of all, there's nothing like outside and inside, right?
Yes.
And the energy dissipation due to the electrical energy, I mean this resistance of the wire of the everywhere, so that electrical energy which you're consuming is also thrown outside. So there are two types of heat dissipation. One, what you consume, take inside and throw outside, but that is coming back actually. So it means that energy cycle is balanced. So every power which you consume from the electricity, that power dissipation will only appear in the kitchen. Understood? See, there is a price you pay to pull the energy from inside and throw outside. So that price is already there. And now what you're throwing outside is going to come back from the door itself, because it is open now.
Yeah.
So cooling is gone, no?
Yes.
You have to throw and you have to prevent it, prevent that energy from coming within inside the refrigerator. So we have to hold it outside only. That's why you keep the door shut. And then heating due to the current flow, that power I square R which you have studied, that heating is also happening. So kitchen will receive how much energy? I square R, isn't it? How kitchen will be cooler? Tell me. Understood what I'm saying?
Yes, sir.
Yes.
Yes.
It is like, I mean, you have a room, okay, and yeah, if I give you ice cubes, okay, and you what to do, you throw the ice cubes out of the room, and then someone is bringing it back. So ice cube is anyway conserved. Same thing like this. Energy is thrown by this coolant system, but if the door is open, so it will come back. Okay, you haven't seen the refrigerator when it is switched off. If you have a refrigerator it is switched off for a long time, and you open the door and switch on, nothing will happen. Except the place close to the coolant will be, colder. But the overall energy which will come outside is the heat energy, and therefore the kitchen will be warmer. So refrigerator is the way to create I mean, of course, these doors are designed so that you have a closed system. You open it when it is required, and then you close it down. Understood? Anyway, I think, do we have
Sir,
more?
I don't understand the part where, like, if we keep the door open, the kitchen becomes more warmer.
Because the heat energy due to the electricity it is already going to the kitchen.
Yes, sir.
So that is extra energy, na?
So, but initially it was not going.
No, it is happening initially. Also. The kitchen is anyway warmer because of the fridge. Do you know this?
Sir, yes, sir, because it absorbs the heat from inside its system and throws it outside.
No. That is different thing. That is happening through the sink, this part. The sink, the heating is due to the flow of current only. In a wire, when current flows, what will happen? Tell me.
Sir, heat is dissipated.
So that heat is different, na? That
Yes,
heat
sir.
is not the heat of the what is thrown by the compressor. The sink. This is the heat sink. Do you realize this?
Yes, sir.
So heat sink will throw the energy from food items outside. I am talking about the I square R. So
Yes, sir.
that I square R is anyway coming. So your kitchen will be hotter only. Whether you open or close doesn't matter.
So, but relatively,
No, nothing. See, it will appear that in the beginning it is so. After some time, it will be heating only.
oh, okay.
It
So,
is like,
sir,
see, you take an ice cube. It is cold. Put
yes,
in your room. It will melt down.
yes, sir.
Will go back to same temperature.
Yes, sir.
What about after that?
Nothing.
Its temperature will rise with the surrounding temperature, isn't it?
Yes, sir.
So when you open the fridge for the first time, it is definitely cooler. So it will take some time to first come to the normal temperature.
Yes, sir.
Then after that, it will heat up. So
Yes, sir.
your experience is based on the initial effect, not the overall effect. Understood what I'm saying?
Okay. Yes, sir.
Yeah, I mean, your perception is because of the initial effect, which you have somewhere in your mind, isn't it?
Yes. Yes, sir.
Yeah, that is happening. Don't worry. All right, guys, let me explain the clauses. It should be just let me have some water. Okay. So let's try to put this clauses statement here. What clauses said that no thermodynamic system, no thermal process is possible where heat flows from low to high temperature without application of external work. Now, heat, the natural process is to go from high to low. So if you want to throw it from low to high, then this can be achieved or accomplished by the extra work. So the refrigerator is consuming the electrical energy. That electrical energy is doing that extra work. Do you realize this? Hello, hello.
Yes, sir.
So that someone must be there to do this extra work. But the thing is, how this extra work can make this again possible? The answer is by doing the extra work, we raise the temperature of the engine. So for the energy to be thrown to the sink, which is, let's say, your kitchen or the surrounding, the compressor is raising the temperature more than surrounding. And so it is able to radiate naturally. Now, this is the interesting part. How you are achieving this task? First, you are taking the energy from the food items inside the refrigerator, and you are raising your temperature to a high value. But because your temperature is more than the surrounding, you radiate naturally. Are you guys getting what I'm saying?
Yes, sir.
Eventually, it is the natural flow. See, your refrigerator, behind the refrigerator, what you are seeing, that diagram which I have shown, the wire mesh, that is radiating energy naturally, isn't it?
Yes.
So actually, energy taken by the compressor is actually absorbed by those heat sink, the wire mesh. But the wire mesh will release that heat to the kitchen or to its surrounding naturally from the high to low formula, the same formula. So in the beginning, you need to do the work. Okay. So like, okay, I was writing this. No? Let's put this. Oh, I think I wrote something. I don't know. So no thermodynamic process is possible where heat flows from low to high temperature without application of in other words, for proper working of heat engine, at least two thermal reservoir are needed. So what is thermal reservoir? Let's put the definition. Tell me guys, what is thermal reservoir?
But it has a large heat capacity.
Yeah. So theoretically, we say that it will have the infinite heat capacity, which means no matter how much energy you give or take, its temperature is going to remain constant. Now we know that the global warming is a big issue, because with the rise of global warming, the natural sink which we take for granted, the atmosphere, although it's a reservoir, but temperature is changing. So over, I mean, every decade, this temperature if keep on rising, even by 1 degree, that is very, very, very dangerous and will destroy the entire vegetation on the earth. So 1 degree is not small. The global temperature rise of all, I mean, 1 degree is already done actually. Now I think we are into the 2nd or 3rd degree actually. And after 4 degree, you know what will happen. So what is the normal body temperature for healthy human being? 98.4, 98.6, I mean, Fahrenheit.
Yes, sir.
And the person will die at 108, in fact 106 also, right? What is the
Yeah.
difference? Do you realize the difference? Only 8 degree difference. In fact, 102 degree fever is also not good, right?
Yes,
So
sir.
imagine a body temperature rising by 5 degree or 4 degrees, so dangerous. So what will happen if the global temperature will rise by 5 degrees? The civilization may collapse. That is why the zero carbon emission is the biggest priority in the world. The sustainable development is the biggest priority. The green fuel is the biggest priority. And every country is incentivizing the green fuel, the EV technology, the electric vehicles. Because people, those who are like illiterate, they know that the impact, this is not some joke. I mean, we will not survive if this will keep on happening at this rate. The world in which we have taken things for granted is not granted. After some time, everything will get affected. Your life, my life, everyone's life will be affected. So we have to be really conscious and careful that in future we have to actually somehow decrease the greenhouse emission. And it is not only caused by like one thing. It is not only vehicle. The carbon emission is due to the industrial development. So in the world, it's something called carbon credit, right? So the rich country buy the carbon credit from the poor country. They give them money and they produce them, make the product and sell in the market. So this is not good. The future is going to be very dangerous. So thermal reservoir is like you can think like a pot which can store energy and having infinite heat capacity, which means any amount of energy given or taken from the reservoir will not change its temperature. So that is what we have to assume. Okay. So that is any amount of heat given or taken from thermal reservoir will not change its temperature. So there are types of, we have two types of thermal reservoir. So what are the types of thermal reservoir? The first is source. So it is called the high temperature. And the sink. Sink doesn't mean that we have to throw energy there. Sink means it is the low temperature reservoir. Okay. What is heat engine? What is heat engine, guys?
Where it is used to produce mechanical work.
It is the device which converts the
Heat
heat
into
Heat energy to
mechanical energy.
mechanical energy.
Very good. Okay, fine. So we have seen that work is converted into heat in the initial chapters itself. In every chapter, we have seen that in current also, the work done by the cell converts into energy. So it was natural to think that if work can be converted into energy, then can we do the reverse? Can we use the heat and create work? Okay. And for that, we need some working substance. So what is working substance? So working substance is the substance which we insert in the engine, which can expand or can be compressed. So generally we take the liquid and gas as the working substance. You can say working substance here is the what we call in commercially fuel. So the fuel is called the working substance. So you know that we have the CNG, we have diesel, we have petrol, we have aviation petrol, which is even higher grade quality petrol. So working substance is anything which you put into the engine, and through that substance we attain the work, because it can expand or it can be compressed, and by attaching the moving system we can create the push. Okay, so anyway, you can say working substance is anything which we use within the heat engine, anything which we can use in the heat engine. Okay, so far so good.
Yes,
Yes,
sir.
sir.
Okay.
Yeah.
Now before we start the engine designing and all, let's talk about the term entropy. So what is entropy? It is the consequence of second law of thermodynamics. It is the consequence of And the many definition. So I'll give you one interesting definition by E.W. Atkins. Have you heard this name? Atkins.
Yes.
So he's one of the biggest author in the world of chemistry, but has written many books for chemistry, for advanced chemistry, somewhat physics also you can say. Especially there is a special work by the Atkins in thermodynamics. And he says something really interesting, which stuck to me for a long time. So he said that it is the measurement of inverse degree of quality of energy. So energy we know. Let's say, let's pretend we know energy. So if you know the energy, then what is the quality? And when the quality is the worst, then I mean the system will collapse. And it is the general tendency of system to take a given energy and make its quality as bad as possible. So we call it inverse degree quality. So the worst quality is the highest entropy. So quality means like the disorderness you create. Understood?
Yes, sir.
Because if you make the highly disordered system, it is highly symmetric. It means nothing worse can happen. In a way, you go to the worst case scenario, or your approach is to achieve the worst case scenario so that we can be most stable system. Like the system is in the equilibrium, it is in stable condition, because nothing bad can happen to such system. For example, if you look at the household items, all items will have some price. Now, if you take the television and put in the bathroom, will it affect the price? Yes or no?
No.
No, sir.
If you take the refrigerator and put in the balcony, will it affect the price?
No.
If your books are found on the rooftop, will it affect the price?
No, sir.
But is this a good quality or bad quality?
Bad call.
I mean, if I really make entire house into chaos, disorderness, then the probability of finding the book is same everywhere, right? Because now your book can be found in rooftop also, in kitchen also, in bathroom also, bedroom also, balcony also, everywhere, because it is highly disordered system. But now you can see that disorderness making the probability equal, isn't it? Now events are equiprobable, and therefore the disorderness is growing in value. The quality of energy is getting deteriorated, isn't it?
Yes, sir.
Okay, so now there is a definition by me. It is the measurement of degree of symmetry. Okay, maybe this is star. The third definition, which you know, it is the measurement of degree of disorderness. See, let me tell you very frankly, when I was in class 11th, when I heard this entropy for the first time, I was not knowing that how this disorderness is so powerful. And what I understand today. So disorderness is actually very powerful. It brings symmetry. It tells that the nature will have the most, if you achieve the most chaotic composition, most disordered system, it is highly stable, isn't it? Do you realize this? This is highly stable.
Yes, sir.
So the quality means the God has created this universe with the best quality of energy and left. And now the universe itself is trying to degrade its quality because the orderness is not so admirable. Imagine that every living planet, which is like Earth, if every planet in which the life can exist is in one part of universe, and all the rest inhabitable is other part of universe. If all stars are found in the other part of universe but not here, will it be good universe? Let's say all moons are at one side, so you have access to nothing. But when you go to your rooftop in the clear sky in the night, you see many stars, you see many planets, and you also see many cosmic events like, I mean, what we call comets and all. You also see the breaking of star also. So what you're able to see everything at once, right? So you're seeing the ordered universe or disordered universe?
Yes, sir.
Disordered.
Of course, disordered. If everything is ordered, then can we see everything at once? No. So the disorderedness is powerful. It's really powerful. It's a big thing. Anyway. Now, absolute entropy is again immeasurable. And I'll tell you something like that. How many ways you can arrange n items? In how many ways you can arrange n items? N
N.
distinct item.
N factorial.
Now, how many numbers we have in the universe? How many things we have in universe? It is, I mean, beyond imagination. It is so. If I take the factorial, what we're going to get? Something immeasurable, isn't it?
Yes.
So can we really measure the absolute entropy?
No.
No. Because measurement of entropy means we have to first count the different microstate, and entropy is given by the Boltzmann by the relation S equals to KB ln omega. Omega is this actually. So omega is called number of microstate of a system. So for a small system, this is interesting. But for larger system, this is impossible to measure. So for larger system, we only measure the change in entropy, not the absolute entropy. This is actually on the tomb of Ludwig Boltzmann. So this is engraved. This entire equation is engraved on the tomb of Ludwig Boltzmann. So the study of the entropy is basically, it's again a statistical study. So in statistical physics, you will study in detail the idea of microstate, the concept of ensemble, and so on. But we do have the empirical version. So we do have the empirical relation for entropy change, not for entropy, but for entropy change. And empirical means the proportional behavior we can understand. So change in entropy is proportional to. So one thing we have realized that the more energy you add to a system, it will bring more chaosness, more disorderness, isn't it? So it is logical to understand that okay, the ds is proportional to dq. But what about the temperature? In a calm environment, the change is found to be bigger, isn't it? Hello, hello, hello.
Yes, sir.
And therefore the ds is actually we can add proportional to dq by t. But see, every empirical relation we always try to keep as simple as possible. So we take k equals to 1. And we simply define ds equals to dq by t. The change in entropy is amount of heat supplied to a system at a given temperature. Okay. So you can say delta S is integration of. So that is the definition of entropy which we follow. Now our universe is constantly undergoing some changes, which is always increasing the entropy. So entropy of universe is always positive. Because when I say universe, can we take universe as a system?
Yes.
And if we take universe as a system, is it possible to have something external to universe?
No.
No. So that's why the universe is, if you take a system, it will contain everything, and everything is happening in a way to achieve the bad quality of energy or high entropy. So universe entropy is constantly increasing. It is always positive. But if I break down universe into two parts, system and surrounding, then this is also positive. But does it mean that the system is always positive?
No.
Does it mean that the surrounding is always positive? Hello, hello.
Yes, sir.
So the system and surrounding individually can be negative also, isn't it?
Yes.
What really matters is the
Around does not does it not like include everything?
no surrounding cannot include. No, universe is everything. So surrounding is not everything. System and surrounding together is everything.
I mean, surrounding is almost everything, sir.
Yeah, it is, but not exact. It is almost. But do you interact with the entire universe at once?
No, sir.
So the part of surrounding which you interact with also very small, isn't it?
Yes, sir.
In fact, even if you take the entire Earth as your interaction, are you interacting with the remaining solar system
No, sir.
and the other solar system of the universe,
No.
No,
other galaxy?
no, sir.
So you understand that though the surrounding is huge, but our interaction is not with the huge surrounding, our interaction with the immediate surrounding, isn't it?
Yes, sir.
So system and surrounding can be individually positive or negative, but the sum cannot be negative. The sum is bound to be
Positive.
positive. Okay.
Yes, sir.
So there is something called Clausius inequality. So what we need to understand that there are two types of process we discussed: reversible and irreversible process. And what is the basic difference between the two processes? Can you guess? A process is basically called irreversible because it is natural. And therefore, any spontaneous process, any process which is spontaneous, which is happening. What is the meaning of spontaneous?
No external driven force or agent is required.
So we do not need any external agent. It is happening naturally. And if something is happening naturally, it will lead to the irreversible process only. And because the process is irreversible, the change of entropy of such process is bound to be positive. Understood? Yeah,
Yes.
it is bound to be positive. I mean, we have no control. It is always positive. What is reversible? In the reversible process, this value, if the process is reversible, the change in entropy of interacting system, I mean, the system and the surrounding, which is the inverse, it is zero. So reversible will make sure that you're not going in one direction, because see, if something is reversible, it should go in both directions, isn't it? And to keep both the direction open, we should not make it bad in quality. We must keep it this process reversible so that it can come back to the initial state through the same path. If you make it irreversible, it will go to a better, I mean, stable condition, and it will never return to the same path. So a system is said to be reversible if the entropy change during the system is zero. And for, I mean, system is the system and surrounding, actually both, not system only. A reversible process means the interacting system is taken into consideration as one system, and there we write the equation. Okay. So in a cyclic, I would say rather like this. In a cyclic reversible process, the ds is always 0. Okay. And in a irreversible process, let's say if you make a cyclic irreversible process, then the ds will be positive only. It will be positive naturally. If it is happening naturally, it is always positive. So we have something called Clausius inequality. And what it says that the term dq by t in a cyclic process, if the process is cyclic, which is happening again and again, it can be either negative or zero. When we take equality,
For reversible process, sir.
yeah. If it is reversible, then the dq by dt is exactly zero. It's called the for a reversible cyclic process. So this is called Clausius inequality. I mean, you're not supposed to worry about all these things, but it's good to know. So by knowing the definition of entropy, let me give you the design of heat engine. Okay. So heat engine we have generally designed for the conversion of heat into work, right? So when you solve numerically, how to draw it? So draw a box like this. I mean, you can draw a rectangle also, it doesn't matter. And you will call one part as source. And you will assume the temperature as high. So we are going to absorb the heat from where? So energy will be absorbed from here. We can call dQA. Heat absorbed from source. And once you absorb the heat, it will reach where? It will reach the device called engine. This is the piston cylinder, right? So once you absorb the heat, it will reach the engine part. And this means it is a cyclic engine. It will work in a cycle. And once you receive the heat, you will perform some work. So what you receive is the arrow is towards you, and what you perform is the arrow is away from you, right?
Yes, sir.
And this we call the work done, GW. But because you're not going to consume everything 100%, what you can see? Some energy will be rejected. There must be some mechanism to take the heat away from the engine and throw it somewhere. The somewhere can be your kitchen, the road, the entire atmosphere. And this point is at low temperature. And this is the heat rejected. And this low temperature body we call sink. So from energy conservation, what you can write? So from energy conservation, we can write. Tell me guys what you can write.
Sir, dq is equal to dw plus dqr.
Exactly. So when you're solving the numerical from the second law, you have to always start with this diagram and this relation. Is this clear? So how much work you attend? Work we can write as dq minus. Okay. So how we define efficiency of heat engine? If it can convert all heat into work, it is called 100% efficient. So how we define efficiency? How much work we attain per unit heat absorbed. The same definition I gave in the last lecture. The work upon the absorbed heat we call efficiency, right?
Yes.
Hello guys.
Yes, sir.
So efficiency we can write as dqa dqr upon dqa. And so this is the general formula for efficiency of any heat engine. Now what you need to remember that this formula is true for engine which is following the reversible cyclic process or engine which is not following the reversible process. In both cases, it is true. Understood? It is true in both cases. So this formula, the way we write 1 minus dq r upon dqa for both reversible and irreversible now. There is a special formula for the reversible cyclic process. For reversible cyclic process, we know one thing. What do we know? For reversible cyclic process, what we know? The ds is
0.
exactly 0. If a process is reversible and cyclic, the ds is 0. Look at the question. How much energy you remove from the source? So decrease in entropy of source due to heat absorption can be write as dqa by th, right?
Yes.
Because you are removing, no? You're not adding, you're removing. So this is the decrease, the loss of entropy. But when you add energy, so increase in entropy of sink due to heat, what heat? Absorption, right? Now that is absorbed by the, or you can say heat rejection by the engine or heat absorption by the sink, right? It is about how you take the context. So increase in entropy of sink due to heat rejected by heat engine or heat absorbed by sink. So how much sink is absorbing? How much sink is getting in it?
dqr.
So we can say ds sink is plus dqr by tl, and you can say this is ds source, but we know that the ds source plus ds sink for any cyclic process is always 0,
Yes.
and for acyclic, sorry, for irreversible, for reversible cyclic process, because this is 0, so you can write as minus dqa by th plus dqr by tl, and so you get a very nice relation. So dqa by th is dqr by tl. So dqr by dqa is in the ratio of its temperature only, isn't it? Do you realize this fact? What is happening?
Yes, sir.
Yes. Sir.
Yes.
And therefore, the efficiency formula we can rewrite for reversible cyclic process. So the eta for reversible, we can not only write like this. This is, of course, we can write, but we can also write this as TL by TH. But can we do the same thing for irreversible process?
No.
The efficiency of irreversible is only this much, but it is not equal to this. I'm writing explicitly so that you can remember this distinction. Okay. And what we know that for any irreversible process, the ds is always positive, right? If a process is natural, it is always irreversible. So the entropy will always increase, right?
Yes.
And therefore, we can say that dqa upon th plus dqr upon TL is positive. So you can see that here dqr by TL is more than. So dqr upon dqa is more than TL by TH. Hello, guys.
Yes, sir.
Yes.
So minus dqr by dqa is less than minus TL by TH. If you know the property of inequality.
Yeah.
Hello. So 1 minus dqr upon dqa is less than. Correct?
Yes, sir.
Which simply means the efficiency of a irreversible process is always less than efficiency of.
Reverse. Yeah.
And that is how we define the Carnot cycle. Carnot is the reversible cyclic process. So this is the proof that efficiency of a reversible process is always more than efficiency of. And this is called Carnot's theorem. You can also understand one thing. You know what? The efficiency of heat engine working between the two fixed temperature in a cyclic order is independent of the temperature of source and sink. So we can say it does not depend on the working substance, right? If you remember, generally what you write, if you remember the first law of thermodynamics, for isobaric process, we used to write dq equals to ncp/dt. Or for isobaric, we used to write the ncv/dt. And for other process, we used to write nc/dt, right?
Yeah.
But Cp, Cv depends on the degree of freedom and hence the working substance, isn't it?
Yes.
So efficiency of irreversible process will have dependency on the working substance. But what about the efficiency of heat engine working in reversible cyclic process? Will it depend on the substance? So the answer is TL by TH. 1 minus TL by TH. So does it depend on the substance what I'm using?
No, sir.
In the reversible case, the dependency on the substance is gone away. The dependency is only for the irreversible process. And this actually is the carnot from which you can rewrite as Carnot's theorem. What Carnot said that, see, if you have a set of heat engine, and if every heat engine is working between the two fixed temperature, TH and TL, then every engine, no matter what they consume, which fuel they consume, the efficiency, the efficiency will be independent of the working substance. All will have same efficiency because all efficiency will depend on only TL and TH, isn't it? Hello, hello.
Yes, sir.
It is clear, guys? Tell me.
Yeah.
Yes, sir.
Okay. So let me put this here. The efficiency of heat engine working between same fixed temperature of source.
Sir,
Yes.
sir, the about three equations that you had written,
Yeah.
what
this is a-
conditions could they be applied, sir?
Pardon?
So you said that these were for like irreversible processes.
No, no. What I'm saying that this dq in general depends on the working substance, right? The
Yes, sir.
for if you have a system and if you see, of course, here you're not changing the temperature, but if you are taking energy from somewhere and giving to a heat engine, the heat engine will work and that will depend on the gamma of the gas. That's it. Okay.
Yes, sir.
And what I'm saying is not this. I'm saying that in the formula of efficiency, we have actually this formula, right?
Yes, sir.
This is equal to this formula only for the reversible cyclic process.
Yes, sir.
For irreversible, it is still this much only, right?
Yes, sir.
And the heat process, you see, the heat taken by the system, the dq depends on the working substance. Okay. I mean, the heat given to the engine, the heat rejected by the engine, it will be function of the working substance. The efficiency will depend on the working substance, but not for the reversible cyclic process. I'm not saying that you use this formula here. Of course, you can't use this formula because here we are extracting heat from where? From where? The source and the sink, right?
Sir, yes, sir. But in those three formulas, what do we do?
Nothing. When you have to just remember that if it is irreversible process, then the efficiency will depend on the substance itself.
Okay, sir.
I mean, of course, it will depend on the heat amount absorbed and rejected, but heat you take, but eventually you give heat to what? The heat engine. And heat engine will have working substance.
Yes, sir.
So when that working substance will take the heat, it will behave differently as we change the working substance. So let's
Yes.
say there is a heat engine with oxygen, there is a heat engine with hydrogen, and you give energy dq externally. Okay. Then
Okay.
the gamma is different for each gas in the different engine.
Yes, sir.
So the efficiency of such engine will depending on which gas you use. Because as you change the gas, the work will change, no? The dW will change.
Yes, sir.
But that is not true for the reversible cyclic process. So in the reversible cyclic process, the heat exchange are done in such a fashion that as you keep on changing the working substance, the exchange of heat will take place in such a way to maintain the efficiency by some mechanism. And how it is done, we don't know, but it is done like this. Theoretically, we know that it should be done like this for any reversible process. Is this clear?
Yes, sir.
So the efficiency of heat engine working between same fixed temperature of source and sink remains the same. And is independent of working substance of engine. Okay. So I hope this is it's okay. Also, you should remember that I have proved that the since eta reversible is more than eta irreversible, right? So if we have the many engine working between the same TH and TL, among all heat engine, the Carnot cycle will have the maximum efficiency. That is also one theorem. The efficiency of Carnot cycle is maximum. So Carnot can give you, I mean, the way Carnot designed the cycle, it is maximum. Okay. So we'll talk about the Carnot cycle. I will tell you, okay, what you are supposed to remember. The only question that you should be aware of is this. That's it. So this is the very, very important. This relation is important. And then second is this relation, the efficiency. Apart from this, you do not need anything else to solve any question of JEE-Mains or advanced, both. So let's talk about the Carnot engine. So Carnot engine is the 4-stroke engine. The first stroke is, have you seen the old scooter anyone? The old scooter with kick.
Yes, sir.
So when you kick the scooter, this is called the first stroke, called the compression stroke. So that is connected to the piston. When you kick, actually you compress the piston. And it is basically, technically it is called adiabatic compression. The second stroke is called ignition stroke. So once you compress, there is a spark plug which is connected within the engine. And when the compressed gas, okay, comes under the spark, and the spark plug is nothing but a capacitor. So the spark plug will get some current, actually, it is getting charged through battery also. So when the spark plug will create some spark, the fuel will catch the fire. And after catching the fire, it will start expanding, which is the third stroke. So we have the ignition stroke. And this is the poor thing. This is the reason behind the failure of the Carnot cycle. So he took the isothermal heat addition. Now tell me guys, if you add heat isothermally, then the addition should be very small and slow rate, right?
Yes.
Yes.
Because when we add heat, temperature will rise, but if we want isothermal, and that's why this is not the practical process. So isothermal is, of course, it's a valid thermodynamic process, but in case of heat engine, it cannot be achieved. And therefore, if you want to design any practical engine in your life as a mechanical engineer in future, you have to only remove the isothermal, add whatever you want, remove it, and you can actually design an engine. The third step is called power stroke. So in the power stroke, what happens? The fuel has burnt already and now it is going to expand. So we call this as adiabatic expansion. And when the piston will pump out, it will force the crankshaft, which will turn the wheel, and the wheel is connected to the chain system, which in turn will move the actual wheel of the scooter or bike, and it will start moving. Then of course it will create rotation, and the rotational effect on the wheel will create the frictional force between the ground, and that friction force will move the bike eventually. So it is not the engine which is moving the bike. What is moving the bike? Forward
Friction.
friction. So what the engine is doing?
Providing the energy.
Of course, it is providing energy. What else? It is giving the rotational motion to the wheel, omega.
Yes.
So and the last stroke, this is called the so the unused energy should be thrown back to the sink, right? And again, there's a problem. This is the isothermal heat rejection. And you can see, guys, that we have two adiabatic and two isothermal processes. Can you plot the graph?
Yes, sir.
It's very easy. So plot the PV graph, how it will look like. So in case of adiabatic and isothermal, we know we plot these two lines for the expansion, and for compression, what we do? Something like this, right?
Yeah.
The first is compression stroke. So it means if I start from here, I can compress, and we have to compress adiabatically. So which graph? The bottom of the top graph.
The lower one.
The top one.
The top one, it's adiabatic, no?
Oh yeah, sorry.
So it is the so when you compress, you go to the the top one, because it's adiabatic compression graph. You reach here A to B, but then you add the heat isothermally. So it means if you add heat isothermally, what will happen? The temperature will be fixed, but as the pressure will increase, volume must decrease because PV equals to constant. So from B to C, you can see volume is decreasing and so the pressure is increasing. That's correct.
Yes, sir.
And because pressure, you see here it is adiabatic. So this point B, what do you think? What temperature is at B? The high or the low? So B will be at high temperature because after compression, the temperature will increase. This is the high temperature, but isothermally, the temperature remains same, isn't it?
Yes, sir.
Then C to D, what will happen? Which process?
Adiabatic expansion.
Yeah, this is the power stroke. This is the power stroke. And so in the power stroke, when we expand adiabatically, you go to the low temperature, and this is where you attain the TH. And
Sir,
then
TL, right?
TL, sorry, TL. And then from D to A, from D to A, what will
Isothermal
happen?
heat rejection.
It is isothermal. So this is also TL, no?
Yes.
So graph is clear to all of you guys. Tell me.
Yes.
Okay, where we are adding the heat, if you remember, this is the heat addition. DQA, isn't it? Hello, hello, hello. And where is the heat rejection? It is here. Tell me,
Yes, sir.
it is clear.
Yes, sir.
Yes.
So we can actually deal with it. I mean, we can write the entire process. In fact, we can derive the efficiency of current cycle from this relation, which is 1 minus dQr by. This is for any cycle we want. Let's see if this process is giving you TL by TH. Yes or no. We have to find it, right? So we have to find somehow the dQr and we can have to find the dQA. So dQA, okay, you can find dQA from B to C. Isothermal process means du is 0, right? So for B to C, du is 0, guys. Yes or no?
Yes, sir.
And therefore the dQ is same as dW. Hello, hello.
Yes, sir.
And we know that dW is how much?
NRT.
NRT ln PV by PC or NRT ln VC by VB.
Yes, sir.
So now this is the dQA. I hope you remember this formula.
Yes, sir.
So you can write the value. I mean, of course, there are two ways of writing it. Well, that's okay. What about the dQr? So for dQr, what we can write? Which is D2A, no? dQr. So to find the dQr, first of all, let's find dQ first for the process called D2A. For D2A, the dQ is same as du, right? Hello, hello. Oh, sorry, dW.
Yes,
Yeah.
sir.
Because we know it is it is isothermal, so du is 0. So dQ we can write directly as dW, correct?
Yeah.
And the work we can write as what? The work we can write as NRTL, right?
Yes,
ln
sir.
VA upon VD, I think. Let me see.
Yes, sir.
Okay, fine. But we know because this is the heat rejection, this answer must be negative. So can we say that dQr, the value of dQr is how much? Minus dQ?
Yeah.
Because this answer is negative, so to make it positive, I have to take it minus sign. value wise. So we are writing value wise. I hope you are getting this. Because how we understand if something is rejected, we know the answer must be negative.
Yes.
But this is already positive only. D to A, it is positive only. But it is rejected, so it must be negative. The answer is positive, it is heat absorbed, so let me get heat release somewhere. Anyway, we'll see. Okay, I'll see. Okay, if I need to change something. But the problem is, if you write the efficiency by the relation, which relation?
1 minus dqr.
1 minus dqr, which is nr
TL.
TL. I think the VA is more than VD, right? This is already positive answer. I mean, we should not change the answer because V is more than VD, right?
Yes, sir.
Upon NRTH, and then what is the next? ln
VC by VD.
VC by VB. That I have, okay, that I have to change because that is negative answer, right? But we have to take only positive value, no? Because that I have to change it. VB by VC, right? Which one is bigger?
VP.
B, no? B, yeah. Okay, this is, I mean, you have to just be careful that, okay, we have to write the positive value, that's it. So once you write the positive value, the answer is how much? 1 minus TL by TH into ln VA by VD upon ln VB by VC. And these things we can correlate easily with the help of process. Understood? So let's write the okay, where A and D appears, you can say look at this process, the adiabatic process. In the adiabatic process, we can write the TV per gamma equals to constant, right? T per gamma minus 1. So from B to C, sorry, from A to B, what we can write? For AB, what was AB? Adiabatic compression, right?
Yeah.
Yes, sir.
So TA VA per gamma minus 1 equals to TB VB, isn't it? And T and TB is how much? If you remember, TA is T and TB is TH. TL, VA, TH, and for C to D. For C to D, guys, tell me what we can add. TC, VC, gamma minus 1, TD, VD, gamma minus 1, isn't it? And TC is how much? TH.
TH.
And TD is how much? TL.
Yes, sir.
So I'll pull, okay, I can add this TL, VD, this real. And now I can do the last step. So 1 divided by 2. TL gets cancelled, so what do you get? VA by VD power gamma minus 1 equals to VB by VC power gamma minus 1. So now power gets removed. So VA by VD turns out to be VB by VC. And because this is equal, what does it mean? The ln VA by VD is also same as ln VB by VC, right? So from A and this B, can we say efficiency is only 1 minus TL by T, because that will cancel out, isn't it?
Yes,
Hello,
sir.
hello. So you can see that the carnot efficiency is the efficiency of a reversible cyclic process. And through the Carnot theorem, we are getting the same answer as we got the entropy relation. That's a shortcut, right? If you remember the shortcut.
Yes.
So the last thing. Okay, how many processes we have? So you can see the ds we write as dq by t. So dq we can also write as tds, isn't it?
Yes, sir.
So dq is nothing but the area under the which graph? TDS graph. Oh, so TS graph, right? So in such case, because we are dealing with the adiabatic and isothermal, and if you remember, the adiabatic process is nothing but the which process? Isentropic. Adiabatic is same as isentropic process, if you remember.
Yes, sir.
So 2 of the adiabatic we can replace by 2 of the isentropic process, isn't it? S1, S2, these lines represents which process? Tell me, guys.
Adiabatic process, sir.
Yeah, and these 2 lines?
Isothermal process, sir.
Isothermal process. Very good. So is this clear to all of you? The process name? Tell me, what is the A to B? A to B was adiabatic compression.
Yeah.
And in the adiabatic compression, the temperature has increased, right? We have gone from the TL to DH. So temperature must increase in the adiabatic compression from TL to TH. So I think this is AB, right? And from B to C, what is happening? If you remember, B to C was
Isothermal addition.
isothermal at high temperature, right? It is
Yes, sir.
isothermal at TH, na?
Yeah.
And from C to D is adiabatic expansion. And go from the TH to TL back. And then D to A is isothermal heat rejection, in which entropy decreases, right? So this is the equivalent TS graph for the same process. And now instead of doing that rigorous calculation, you can write this way. So tell me, guys, where you added the heat? You added the heat at high temperature here. And where the heat was rejected? Am I right?
Yes, sir.
Yes, sir.
Because the heat addition or the heat rejection occurred at constant temperature, right? So we have this relation. So dqa can be write as area under the graph is how much? pH into S2 minus S1, because we are writing the value, isn't it? Hello, hello. Area under this graph, this area is how much?
pH is 2 minus S1.
So this is the area, no? Because what is the definition? The dq is nothing but the area under the TS graph, isn't it? So this is the heat addition. What is the heat rejection? This area. You realize this.
Yes.
So the dqr we can simply write as TL into, we are writing value only. S2 minus S1, right? Hello, hello, hello.
Yes, sir.
So efficiency is how much? 1 minus dqr by dq. Yeah, and the answer you can see clearly it is. So this is the easy derivation. And the previous was the actual PV graph derivation. And we have done one more derivation much before, right? In the very beginning. So I hope this is clear. Hello, hello, hello.
Yes, sir.
Yes, sir.
So now we have just two more, and we are almost at the end of this thermodynamics. So now we have the refrigerator. And heat pump. And the coefficient of performance. Okay, so I'll start with the coefficient of performance. So it depends on what we are trying to define. So we'll talk about the refrigerator. So refrigerator or AC. Both works in the same way. So AC cools your room, right? So what AC
Yes,
does,
sir.
it takes heat from your room and throws to the outside, isn't it? Hello, hello, hello. So what AC is doing is the same thing, no? What refrigerator is doing, isn't it?
Yes, sir.
So your room is like a big refrigerator, so you can call AC. The refrigerator is a small room, which you call refrigerator. Anyway, the way you can think. So what we are doing, the energy we are snatching from where? Low temperature or high temperature?
High temperature, sir.
So I think you are always thinking in a different way. When your room is, when you enter the room, switch on the AC,
All
what
right,
you
low
want to,
temp.
yeah.
Yes, sir.
So at equilibrium, the temperature of the room is maintained at low temperature. So it is constantly taking the energy and throwing outside, right? So that the temperature remains same, the low.
Yes, sir.
So in the refrigerator, the rule is we do the reverse process. And to make the process reverse, we have to reverse the direction of work. So earlier the engine was working, but now the engine is replaced by the compressor or whatever. And we have to change the arrows. So can you tell me where is the refrigerator or your room? Top or bottom?
Bottom, sir.
Is source or sink where you're living now?
Sir, we are living in the lower temperature region.
Yeah. So okay, you should not say sink, right? Yeah. So you're living here. This is your refrigerator. The sink behaves as a refrigerator. Do you realize this?
Yes, sir.
Now, the moment you use the refrigerator or the heat pump, it will reverse the arrow. So you take the energy from here. What I will do is I'll keep the sign intact. Symbolically, I will keep it DQR only. And the work will change the arrow. Earlier, the work was done by the refrigerator. Now, I'm sorry, by the engine. Now we have to do the work on the engine to get it reverse process. So this is the DW. And this will be the DQA. So first thing that you need to remember that when you design the refrigerator, you have to draw this diagram carefully. Okay. Once it is done, the energy consumption will be same. So it is still the same equation, isn't it?
Yes,
And if we write the energy consumption for this engine, so energy received is this much. Sorry. This is the energy received, isn't it?
Yes, sir.
And what is the heat rejected? I mean, the heat thrown outside?
DQE.
Yeah. Not only what you take out from the room, even the heating produced by the electricity, that both energy it has to throw out. And now you can understand that why they are able to cool. They are not only throwing the food item energy, they're also throwing out the energy which they produce by the virtue of heat. Understood? I mean the current, the electrical energy.
Yes, sir.
Clear? Okay. Now here we don't define efficiency, we define the coefficient of performance, COP. How well your refrigerator is performing. So how you will rate your refrigerator on basis on what basis? So to make your refrigerator work, you consume the electrical energy, which is dW. So this is generally from the electrical supply. So to make this possible, you do some work, right? So a good performing refrigerator will require less work or more work. A good performing refrigerator will require less work or more work.
Sir, more work.
Hmm. You want to pay more bill.
Oh, no, sir.
Okay, what is your job? You want to throw the energy out of your room or out of the refrigerator, right?
Yes, sir.
So a better performance will have more DQR or less DQR.
More DQR, sir. Oh, right. Yes, sir.
So we are talking about performance, like how well my refrigerator is performing. So to make this throw out, you're doing some work, right?
Yes, sir. So, sir, it's like for a unit amount of work that the refrigerator does, how much heat does it throw out?
Exactly. And not throw out, throw away from the sink. Because the total energy the engine is throwing out is this much, right?
Yes, sir.
So how much heat you extract from the room or the refrigerator per unit work done is the performance, right?
Yes, sir.
Are you guys getting this? It is different from efficiency. Efficiency is defined in a different context. Here, the efficiency what will have no meaning. Efficiency we define for the heat engine in which we give energy and we wait for the work, how much work it is performing. Here we are doing the work so that the energy extraction can take place. And when say we are doing the work, it means it is the electrical energy doing the work. Understood? Hello, hello.
Sir, here we are, by coefficient of performance, we are defining the quality of the engine, sir.
Yes, you can say so. The quality.
Okay, sir.
So if you understand the purpose, it is easy to define.
Yes,
What is the purpose here? Purpose you understand? You all?
yes, sir.
Yes, sir.
Yes, sir.
And to achieve the purpose, you are doing work now this time, right? This arrow is saying that we are working on the engine, right? Earlier work was done by the engine, but who is doing now? First we are doing the work, then the engine is doing, of course, later on. So this is coming from the electrical energy consumption. So you may be given that if the power of the electrical supply is given to you, so you can add power into time as energy and you can express the answer. Okay. So if we can also decide dqr by dt upon dw by dt, right? Which means at what rate you throw the heat outside, right? So this becomes the heat rejection rate or heat, heat extraction rate. This is the heat extraction rate upon electrical power supply, isn't it?
Yes, sir.
So either you can express in terms of energy or you can express in terms of power supply. So you have to just divide by dt, both sides it is possible. But anyway, let's go back to the first relation, dqr by dw. But how we can add this as? This is always this much, right? So COP of REF is equals to 1 upon dqa by dqr minus 1. Hello.
Yes, sir.
Yes, sir.
Okay, so we know the efficiency relation, right? So can we compare the or relate the efficiency here? So I can add anyway 1 upon or not 1 upon COP of refrigerator is how much? dqa by dqr minus 1. And dqa by dqr is how much? It's efficiency is 1 minus dqr by dqa. It is all about manipulation. This is equals to 1 minus eta. So eventually then. So C1 upon COP of a refrigerator is how much? 1 upon 1 minus eta minus 1, right?
Yes.
It is 1 minus 1. Eta upon 1 minus eta. Whatever. I mean, no need to mug up this formula derived in the examination. So this clear? So if you know the efficiency, you can find the coefficient of performance of refrigerator directly, right? This is better way of writing. So okay, I can see finally the answer is 1 plus COP of a refrigerator is 1 by eta. This is the answer coming, right? You can check. Yeah. 1 plus COP of refrigerator is inverse of efficiency. So basically the coefficient of performance, what you are getting, it is more than 1, right? You may consume 1 unit of power and you may throw much more energy outside. That's what possible, isn't it? So performance need not to be less than 1. It could be anywhere. It could be 10 times, 100 times also. Now, what is heat pump? So in the cold countries, let's say if you go to Russia, Canada, so they have the centralized heating system. Just like we have the cooling system. So they don't use the individual heater. So they keep the entire building warm. And that is the requirement. If you go to even Europe, anywhere in Europe, then in the winter, it may be very cold outside, but people don't live on the road for a long time. Hardly they move out of their home for 5 to 10 minutes. And the moment you come out of your home and enter any restaurant or any cafeteria or wherever, the entire ambience is very warm. So you can just take out your jacket also, even in the the coldest winter also. So heat pump, is a designed to, create every building. It's the reverse of AC, you can think of. So what we do here, we do the reverse process. The building is here. And the outside is really cold, isn't it? It's very cold outside, almost frozen. But still, what you are doing here? This heat pump is taking energy from where? To keep the room warm, what will do? You will take the energy from here and will throw in the room itself. Yes, you can understand this way. So if you design the heat pump, so you live in a high temperature or low temperature region? Where you are living now?
High temperature region, sir.
Yeah. So your room is at high temperature. So now you live in the source. So this is the, I mean, what you can say, room. So when you switch on this heat pump, you will take the energy from the atmosphere by doing the work on the engine, and eventually the energy due to the heat dissipation of current and the energy which you withdraw, both together you will throw back into the room. So room will get how much energy? So the first equation is always same. It is dqa is dw dqr. This is always you have to start with, and then the FSM, the performance you can define. So tell me how you will define performance here.
Sir,
So coefficient of performance of the heat pump will be, yes. Tell me.
sir, is it DQR?
See, wherever you are living, think from that perspective. You get the right
Oh,
answer.
it means it would be DQA by DQW.
Correct. See, eventually you are receiving this much, so you are happy, na? I mean, does it matter that who is giving you energy? You want more energy? That's it.
Yes,
You
sir.
want to make your room warm. So will you complain if someone else will give you energy?
No, sir.
So what really matters is what is the net energy received by the source, right?
Yes, sir.
Per unit work done on the device, the engine. Isn't it? Hello, hello.
Yes.
So it is simple. This answer is simple because this is inverse of what we have done already. So in the heat pump case, the dqa, and this you can attach dqa minus dqr, which is exactly 1 minus dqr by dqa, which is exactly 1 by eta. So for heat pump, the inverse of efficiency is coefficient of performance of heat pump, and 1 plus coefficient of performance of a refrigerator is inverse of eta. Isn't it? So, and the eta is 1 minus TL by TH, and dqr by dqa is TL by TH. Let me tell you, if you want to solve any question of JEE-Mains from this second law, only these 4 equations you need. That's it. Nothing else you need. And of course, you need one more equation. With this 5 equation, you can solve any question, whichever is so far asked in the examination. It's clear? Hello, hello, hello.
Yes, sir.
Yes, sir.
Okay, so I'm done with the chapter. So this is the end of the second one. Let's see some question. Want to see some question?
Yes, sir.
Yes.
Okay. So can you see, tell me the page number?
183.
180. Wow. See, if you see the question, you can directly correlate. Everything is plot, right? Can you
Yes.
see it? Every question we have done. In fact, 15 questions we did today also, right?
Yes.
And the same question I taught, actually, this question I taught in 2013. Yes. Eventually it came in 2020. Good. You can see all this process, okay? The graph, I think you should not be fearful of the graph, right? Yes. So, any question you can take. Solve the first example first. A gas can be taken from A to B via two different process A, C, B. Okay, they should put the arrow actually. Oh, just I'm going to share first. Okay. Can you see this now?
Yes.
So a gas can be taken from A to B via two different processes, ACB or ADB. When path ACB is used, if you use this path, the top one, 60 joule of heat flows into the system. So dq is given, absorb is, and for the path ADB is and 30 of work. So du is how much? Du is how much? Tell me. 30.
60 minus 30. Yes, sir.
So that's part is, but du remains same, no? For A to B, no matter which path you choose, the du will be same.
Yes, sir.
So now they're saying the if the path ADB is used, work done by the system is 10. So work is 10. But du is same. So what is the dq?
40, sir.
Such a simple question they ask, right? Solve the question number 2. 200 gram water is heated from this to this, ignoring the slight expansion of water. The change in its internal energy close to, given the specific heat of water is given. So how much energy it is going to absorb?
16.7, sir.
How much? 167. That's 16.7. Yeah, maybe. So it is
No, sir,
simply
it's 160,
MS.
sir.
It is MS delta heater, right?
Yes, sir.
So mass is given. How much is coming? S is given.
16.7, sir.
Okay, that's coming. Okay. 6 into 4. So how you got the answer? Hasika?
Sir, 20 by 5 into 4.2.
20 over 5 into 4.2 into
Sir, that's it, sir. I mean, like 4.2 kilojoules.
yeah, I think the MS, but the temperature changed from 40 to 16, no?
Yes, sir.
So which formula you use? M into S.
Sir, MS delta T. Yes, sir.
Delta T is how much? 20, no?
Yes, sir.
Okay, you use that value 20?
Yes, sir. I
Okay, okay.
converted.
No. Actually, I took 30. Actually, that's what. Okay, that's what. Why the answer is not
Yes.
matching? Yeah, correct. Okay, anyway. So you can answer the question number 6 without solving.
Option B.
Thermodynamic process. Okay, in the question number 4, it is actually based on the conservation of mole, because it's a closed chambers and all. So an insulated container of gas has two chambers separated by an insulating partition. One of the chambers has volume V1, contains gas pressure P1, temperature T1. Other this. If partition is removed without doing any work on the gas, the final equilibrium temperature of the gas in the container will be. So what we have to do? Conservation of internal energy. Why? Because no work is being done, isn't it? So internal energy of the first and second chamber will be equal to the whole chamber,
Yes, sir.
isn't it? Or also, I mean, of course, you can do the more conservation. That should also give the answer. I think this can be derived in two ways. Because there is no work is being done, right? So I think mole will give you the answer directly because here the N1, N2 is not given. Fine. So we can derive N1, N2. So can you solve this question? So eventually it will have same pressure, right? Same temperature. Because it's only one system, no?
Yes, sir.
And because no work is being done, so we can conserve the internal energy of each system by the relation N1 CV1. I mean, that is not equal. CV for CV, they should mention the gamma also. Leave it. I think more conversion is sufficient. So which option is coming? Tell me.
Sir, could you please show the options?
This is the two options. A, B, and C, D is our.
Yeah, just Sir, I think option A.
Yeah, we can check the answer. It's given. Yes, you cannot check the answer.
One
Okay,
second. Yes, sir. Option A.
Okay. So the next part we can go. This is some different problem. This is question number. Yeah, question number 8. Check the question number 8. 3 different processes that can occur in an ideal monatomic gas are shown in the figure. The paths are labeled A, B, AC, AB. The change in internal energies during these processes are taken as EAB, EFF, so mentioned. Okay. The correct relation is. So you can see there are 2 isotherms drawn, right? And
Yes,
in a
sir.
PV graph, anyway, we know that in a PV graph, these isotherms with high temperature away and low temperature close. So because these are isotherms, so if you go from low to high, internal will increase and high to low decrease. So you can see A to D, A to C, A to B, all are having same difference of temperature, right?
Yeah.
So the internal energy will be same for all, no?
Yes, sir.
Isn't it? And then check the area under the graph for the work done. That's it. Hello, hello. I can see for A to D there is no work done, right?
Yes, sir.
A to D there is no work. A to C will have less work and A to B will have maximum.
Yes, sir.
So you can easily identify the question, right? So graphical questions are,
So
yeah.
A to C will have no work. Volume axis will have like no area under it.
A to C will have negative and positive area equal. I mean, not equal, not equal. This is not equal. This is only half. It's a very vertical. I mean, maybe the graph is not shown correctly. I mean, A to C, how they have plotted. Look at this. This is graph they have plotted. Right? So A to D. So the area, if you look, okay, let me make it more curved. This is better. So A to D, if you go at this point, this is the which work? Negative work. But if you go from this to this point, it is positive work.
Hmm.
So actually, this is the area, no? So it depending on how much is this curve, is it flat or curve? It could be zero, it could be non-zero, but it could be mostly positive. If it is not flat, it is positive, right?
Yeah.
See, I can see there is only one option in which all are this is same. Any other option is wrong, right?
Yes.
I think they haven't done correctly. This is of course positive. This is vertical, and this is horizontal actually. Anyway, so B is the answer. Leave it. The typing is not clear actually. Okay, just a moment. I would like to solve some tough question. There was one tough question. I hope you can solve all these graphical question, right? You can see some unique question. Yeah, 17 question. This is interesting. The 17th is interesting. It is using the the mean time of relaxation and those ideas. Under an adiabatic process, the volume of an ideal gas gets doubled. Consequently, the mean collision time between the gas molecule changes from this to this. Gamma for this gas, then a good estimate of tau 2 upon tau 1 is. Yeah, I think this you can solve. If you remember how to relate the time with pressure, volume, and all, temperature. Do you remember that? I think it was P and T relation, right? Hello.
So relaxation depends inversely of time. Sorry, temperature.
Time, temperature. And proportional to what?
Pressure.
Pressure.
No, I think you're missing something. It was lambda upon
Under root T.
lambda upon proportional to lambda upon what? The velocity, average velocity, and V is under root of T, and lambda is inverse of concentration. And we know P equals to CKT. So the concentration is basically P by T, right? And proportional. So if you substitute this was root 2 into P by T, basically the answer which we got was root 2 E by P. Do you remember this? Of course you
Yeah.
don't remember.
No, I
And
just
okay, if you remember this, then it's easy. So you can also write it in terms of volume, because they want to answer in terms of volume, because what is given? The volume is doubled, right? So volume relation is given to you, right? Isn't it? So PV equals to nRT. So V P we can replace by T by D by V, right? Just replace root P by T by V, which is again V by root T. I mean, all proportional. So the tau 2 by tau 1 is how much? Hello guys, how much? V2 by V1 into under root of T1 by T2, isn't it?
Yes, sir.
And the TV power gamma minus 1 equals to constant. So T1 by T2, V1 by V2 power gamma minus 1 is equals to 1. I mean, you can write like this. So you understood now how to replace this. So T1 V1 gamma minus 1 equals to T2 V2 gamma minus 1. So T1 by T2 is V2 by V1 power gamma minus 1, and we know this answer. Volume is doubled, so this is 2 power gamma minus 1, and therefore if you take the root, it will come by 2. So 2 V2 is 2 into 2 power. 2 power how much? 1 plus, which is going to 2 power gamma plus 1 by 2. I think we might have missed something in writing, but this is seems to be D answer. Maybe up and down, or maybe they have asked opposite ratio 1 by 2, 2 by 1. Can you check the answer? Is it D? Hopefully. The whole idea is eventually convert into P and V, or V and T and whatever, and they will mention the process, you can do it. So this kind of question is very common.
What you have done is correct. In the answer kit is given as bonus, and the
Ah.
answer is 2 raised to gamma plus 1 by 2.
Yeah, I thought that should be bonus only. But none of the options is matching, right?
Yeah, none are matching. The one you have done is correct.
So you can understand that these kind of questions are not difficult. Convert into the relation of PVT eventually, and from there you can derive values. I hope this is clear.
Yes,
No,
sir.
no?
Yes.
So these are unique questions. The rest, whatever you're seeing, the graphical question you can solve with ease. I can do it. Question number 20. In most of ideal gas with constant volume heat capacity CV undergo isobaric expansion by certain volume. The ratio of work done in the process to the heat supplied. Do you remember? Isobaric is very famous, if you remember. You're
Yes.
asking for dw by dq, right? So this is nr dt. This is how we remember. And this is n cp dt, right?
Yes, sir.
Hello, hello.
Yes, sir.
So it is r by cp, but they haven't written answer in terms of cp. So cp we can write as r plus cp. Isn't it?
Yes.
Yes.
So what is the answer? R upon r plus cv, right? Oh, this is interesting. It is volume heat capacity. This will be molar heat. Okay. Anyway, that's mean molar heat capacity at constant volume. I think this is incorrect. N should not come. It is volume heat capacity or it's a molar heat capacity at constant volume. Can you check the answers? I think this should be the answer.
The
Okay.
answer is option A.
A will come, but the N should not come actually.
In the solution, it is written work is nRdt. So heat given will be CV dt plus nRdt. So work
Okay.
by heat given would be the ratio and N would
It
stay
is,
there.
yeah, it is isobaric. So isobaric we can add directly NCPDT. This is wrong. This is wrong. The N will not come. I'm damn sure.
So
Look at the question 21. One mole of gas passes
Sir?
through a process. Yes.
Sir, in the above question, in the DQ formula, we write Cp as molar heat capacity, right?
Yeah, that's why I'm confusing with this. Is this molar or
So,
something
sir,
else?
no, in the question it is given as only volume heat capacity.
That's why
So
this is the
it should be
so it
Cv
is
by N for
correct.
the molar heat capacity.
Is this something there? That's why I thought this is some wrong typo, but anyway. The volume heat capacity means what? It is not molar. So dq equals to, we know, I mean, C is defined as dq by N dt, right?
Yes,
So
sir.
the NC will be dq by dt, isn't it? So they might have given this as C. They can define anything, a volume heat capacity. What is this volume heat capacity? Either it is specific heat capacity or it is molar heat capacity. So it is, if it is heat capacity at per into volume, so is it dq by dv upon dt?
Sir, I think they just meant heat capacity as constant volume, and just to write it in short, they wrote constant volume heat cap.
Yeah, I mean, this is confusing in that way. That's what I'm saying. Yeah, it is heat capacity actually, which is N into C, not yeah, I understood. This is NC only. So our NCV is this capital C, right? So in the formula, what we have to do? Replace CV by
Cv
what?
by M.
CV by
Cv
N.
by
I mean,
N.
this, yeah, by N. This is what is given. So the answer becomes NR by So this is correct answer, but their CV is different from this CV. Volume heat capacity. Okay, fine. It is heat capacity. I mean, if it is just heat capacity, we know the answer is N into C, right?
Yes.
Yes.
Yeah, that's fine. Then this is correct. This is the right answer. So answer is actually R plus the CV, the way we define, and how we define CV? dq by n dt. And if it is only heat capacity, so it is. So they have given this as CV. So if you compare the n of my CV is given CV this, so I have to replace this CV by. Understood?
Yes, sir.
And then you have to put it here, we get the answer. Yeah, that's fine. Anyway. The next question, 21. So this, if you look at the question, you may get confused, but this is very easy question. Why? Because something is given. Calculate the change in the temperature of gas if its volume changes from here to here. So volume is going from V0 to V0, right? So because pressure is given as a function of volume, we can easily find the pressure, right?
Yes,
So what
sir.
is the P? What is the P initial?
P0.
P naught by 2.
It is P0 1 minus 1 by 2 into 1 whole square. It is P0 by 2, right?
Yeah,
And what is P2?
it's coming 7 by 8 P naught, I think.
It is 1 by 2 into 1 by 4, right? Yes. So 7 by 8 P0. Correct? And then write the ideal gas equation. Because anyway, they want to change, no? So T equals to PV by NR, N is given 1. So delta T is how much? P2 V2 P1.
5 by 4
Yeah.
P naught.
Simple. So such kind of question will be very easy. I mean, not at all difficult. Now you can see this question 26. It's directly the polytropic process. Whatever it is given. I think. Rigid diameter. Okay, it's adiabatic process. Okay. So for adiabatic, what is the formula? T power gamma minus 1, right?
Gamma minus
So
1.
X is how much? Gamma minus 1.
Yes, sir.
And it's a diatomic rigidity, which means the gamma will be 7 by 5.
7 by 5.
Minus 1 is
7.
how much? 2 by
2.
5.
2 by 5.
Answer is B.
Yeah.
Yes, sir.
So nothing is difficult. Right? This chapter, I mean, I'm sure that you will be able to solve in function if thermo will come. And the famous question. Do you remember this question? This question is just I was looking for which question. 28. Yes. So you can read the question. 1 mole of an ideal monoatomic gas is taken this path A, B, C, A. The maximum temperature attained by the gas along the path BC. So exactly same question that we did in last class. Hello. So find the PV,
Yeah.
find the PV equation, convert the TV equation, differentiate T, you will get the answer. Correct?
Yes, sir.
Yes.
I hope you can do this. So I'm not solving. I'm leaving this question. This. 29th question, you can do mentally. 1 mole of an ideal. See, it is isothermal compression. So the pressure is, you are going from pressure where to P1 to 2P, I mean P to 2P, right? At 27 degrees Celsius. So use the formula for work. What is the answer? nRT.
Sir, D.
Yeah, that's. And the same question we did in the last lecture, 30th question. Okay. The ratio of work done by the ideal monatomic gas to the heat supplied, isobaric process. Monatomic gas, so we know the answer is R upon CV plus R. And CV is R upon gamma minus 1. So this is, you know how to solve this. Do the 31. Tell me the answer. Every question which I have shown in the class, every theory I have done, it will help you solve every question. So for 31, what is the answer? Tell me, guys. Done? How much is the answer? The same answer, no? N. So this was R by CP, right? And
Yes.
CP itself is how much? Gamma R by gamma minus 1.
Mhm,
So the
yes.
answer is gamma minus 1 by gamma, which is 1 minus 1 by gamma, whatever it comes out. So 1 minus 1 by gamma is how much? It's a monatomic, so 5 by 3. That is
2 by 3. This is 2 by 3.
anyone
2 by
got this
5.
answer? Yeah, very good. So these questions are there. How many questions are there? 70, 80, how many? Let me go first down, let me see the latest. Okay, these are efficiency based question. So I hope you can solve as much as possible. It's a 2-minute question. Now look at the question number 78, which statement is incorrect. So it's a purely Carnot cycle based. It is again 73 Carnot cycle. There are many questions of Carnot cycle. Okay. So okay, this is second law, especially. Second law. Yeah, this is refrigerator. And in case of cascaded system of engines, the DQR of the first becomes DQA of the second, right? Like in 54. So we have 3 engines, E1, E2, E3. Can you see that?
No, sir.
So you mean the 59th one?
Yeah, 59th one.
Acha.
In 59th, do you see 3 engines?
Yes, sir.
So when we have the cascaded system, then the DQR of the first becomes the DQA of the second and vice versa. So the way of attempting will be, you can say DQA, W1, DQR, but DQR becomes the actually DQA of this. So this is, you can say DQR again, DQR dash, you can say DQR dash and DQR double dash. This is how I can also say DQR dot triple dash, something like this. But what they are saying,
condition for equal efficiency, sir.
So equal efficiency means the ratio of 1 minus T1 by Tu2 is same as 1 minus T2 by, I mean, sorry, 2 by 1 equals to 3 by 2 equals to, you can directly write as the T2 by T1 is same as T3 by same as T4 by T3, isn't it?
Yes, sir.
Because the efficiency depends on temperature difference, right? Temperature of the source and sink gas. So equally efficient means they have same ratio of temperature, right? So have they given such an option? Yeah, of course you can derive the relation. T2 square is T1, T3. The first two will give you, right? Hello, hello.
Yes, sir.
And T3 square is T2, T4. I think the option, how they have written it. T3 they have written 1, 4, T3 is actually 2, 4. Let's put it. Then we can put 2 by 1, 1 by 2, 4 by 3. T2 square is 1, 3, and T3 square is 2, 4. Okay, so we have to make the replacement. Let me check again. So T2 is how much? T1, T3 power
Uh,
1 by 2. And T3 is T2, T4 power
uh,
1 by 2. So they're asking T2. Okay, so this we can write as T2 is how much we can write? T1 into, and T3 we can replace by T2, T4, isn't it? Whole power 1 by 2, isn't it?
Yeah.
That becomes T1 power 1 by 2. 2 is coming. Ah, that's right. So we got it. So T2 is how much? T1 power 1 by 2. T2 power, sorry, T1 power, yeah, T1 power 1 by 2. T2 power 1 by 4. And T4 power 1 by 4, right? So take T2 other side, so T2 power 3 by 4 is T1 power 1 by 2. Okay. So T2 is
1 square T4 whole to the power 1 by 3 T2.
2 by 3, no? So 4 by 3 into 1 by 2.
So 1 by 2 to the power 1 by 2, right? 1 by 4.
No, I'm taking T2 itself.
Ah, sorry.
This is right? T1 power 2
So
by 3.
till second last step, it's okay. Just let me check the last step.
Yeah, you can do this. I mean, like, you understood how to replace. You have to match the
Uh-huh.
answer. This is the equation actually. And the rest is the matching answer.
Sir, so it's the second one?
Yeah, you can match. You can check the answer. I don't know. I have to scroll down.
We're getting second.
You can open your mobile phone also, yeah, so that you can scroll it.
Okay.
This is question number 59.
Sir, option B.
But I think you can do this. Eventually, it's a calculation. Rest is directly forward. Rest. Let's see something. Efficiency of this engine is the area upon heat absorbed. So to find the heat absorbed part, so you have to check which process will have of the absorption of heat. I think BC will absorb heat, and that's it. Rest will, the AB will also absorb heat. AB and BC, find the DQ for AB and BC and then add them together. Solve 63. Check if you are getting the answer. See the question. 69. Can you see the question 69? Read it. We discussed today, isn't it?
Yes, sir,
Oh.
option D.
So very interesting answer. There been increase in winters, decrease in summers, remain same, decrease, increase. Yeah. I think every question I have covered in this short lecture. But the thermodynamics of JEE-Mains is quite different from thermodynamics of JEE-Advanced. In an advanced, sometimes it goes really challenging in terms of writing. I mean, it's like too much of writing, too much of manipulation. So after the JEE-Mains, I'll start the, when advanced practice will start, PYQs, we'll see the all the challenging problem from the extra years, especially the advanced, when it was subjective. So we will solve more of the subjective question from the past. To gain more insight into the difficulty of the problem. Also, this is the last question. Let me solve this. So which question I gave? 63, right? An engine operates by taking animals of gas through this CV is given the efficiency. So efficiency is defined as work upon heat absorb, right? Now work is area under the curve. This is how much? 2 P naught minus P naught. So this is P naught, V naught. That's it. So P naught V naught upon. How to write the heat absorb? So right here and right. Okay. So B to C heat is absorbed and A to B heat is absorbed. Yeah, I think they have given a different arrow here. Okay, it is not cyclic. Or is it misprint? I don't know. It must be cyclic, no? Okay, I'm correcting this as cyclic and then solve. So heat absorbed is how much, guys? So work is P naught V naught, and then what we can write? The heat absorbed for the dq plus dq because in the rest of the case I can see clearly heat will be rejected. And it is very easy. AB is which process? Isochoric. So N CV TB minus TA plus NCP TC minus TB. So you have to write like this, and you have to also find the temperature of every point TA TB. So before you start solving, write temperature at every point by quickly writing the ideal gas equation. So P naught V naught upon NR equals to TA, and let's call this as T naught because that's easy to write. So TV is how much? 2P naught
4
V
T
naught
naught,
equals
I
to.
think.
So I think this will become 2T naught, right?
2 T
Pressure is
naught.
doubled. So if I say this is T naught, this is 2T naught, and keeping the pressure constant, if volume is doubled, the temperature will be also double, right?
Yeah.
4T naught,
Yes.
and then keeping the volume constant, pressure is halved. So 2T naught again, isn't it? So it's pretty
Yes.
easy, right? It's a 2T naught, 4T naught, 2T naught. So this you can eventually write P naught V naught upon N CV. We can write as R upon gamma minus 1. CV is given 1. Okay, let's use that. So CV we can write as 1.5 R. And TV minus TA is how much? Tell me. T minus TA is T naught. And in CP is 2.5 R because we have to just add R to CV, right? And C minus B.
Naught.
So our answer is P naught V naught upon how much? 4 no 5 6.5. Just correct me if I'm wrong.
Yes, 6.5.
So it is 1 by 6.5, right? 10 by 65. 2 by 13. How much?
Sir, 0.1.
0.15. B option is correct. Can you check the answer B?
1.
Yes. Option should be 0.15. This is coming now.
Yes, sir. Option B is correct.
So, okay, of course, you have to learn how to write it fast and how to convert things into simpler way. So, some thinking is required. So we have solved the question from second law as well. I'm sure you can do this question, not difficult. This is the carnot and all. If you remember this spin question I discussed, so think about this question as well. The heater will give it BQ, the gas will expand. Okay, the piston will compress the spring. So work done by the gas will be energy stored in the spring, right? That way.
Yes, sir.
So try this. I mean, of course, I'm not saying this 30C. 32 is really interesting. I mean, again, it's a similar to the what we did. 33 is also interesting, and 30, yeah. So 32 and 33. is very, very important. You can try to solve on your own. And then if you don't get it, don't worry. You can ask any. So now guys, from today onwards, what is my session? Revise, and just revise. Whatever you have learned, try to go through the videos. If you are not getting any video, just let me know. Revise as much as possible. Just